Welcome to the course Nuclear and Particle Physics, course code BSCP3051, program name BSc Honors Physics. The topic of discussion is liquid drop model. We will cover the topics: introduction, characteristics of nuclear forces, similarities of liquid drop model, advantages of liquid drop model, failures of liquid drop model, and the references. As a prerequisite or recapitulation, we should have the knowledge of constituents of nuclei and knowledge of binding energy. After studying this unit, we should be able to explain the nature of the forces between the nucleons, the liquid drop model, the basic assumptions of the liquid drop model, and its failures, achievements. Introduction. In the beginning of 20th century, the gravitational and electromagnetic Coulomb forces could not account for the stability of nucleus. Protons carry positive charge and neutrons are neutral particles. There will be repulsive electrostatic force between two protons. So this force should cause the nucleus to break up. The gravitational force of attraction between two nucleons is extremely feeble. So it cannot explain why the nucleus is bound. Gravitational force is significant only on macroscopic scale. When we are dealing with the astronomical objects, the new force called nuclear force was introduced to account for the stability of nucleus. This force was assumed to be much stronger than the repulsive Coulomb force between two protons. This force is attractive between any of the nucleons, whether they are two protons or two neutrons or one proton, one neutron. In 1935, Weizsäcker proposed on the basis of experimental facts that a nucleus resembles a liquid drop. Liquid drop model tries to predict the properties of the nucleus. In this model, the nucleus is treated like a drop of liquid in which nucleons are present in the nucleus, interact very strongly among themselves. Now, we will discuss about characteristics of nuclear forces. First is, nuclear forces are charge independent. The force between two neutrons is the same as between two protons and between a neutron and a proton. This is termed as charge independence of nuclear forces. This is also clear from the formation of mirror nuclei. For instance, hydrogen 3,1 and helium 3,2 are mirror nuclei since their former contains one proton, two neutrons, while the latter contains two protons and one neutron. The binding energy of these are 8.5 megaelectron-volt and 7.7 megaelectron-volt. The three types of nuclear forces, neutron-neutron, proton-proton, neutron-proton, are equal in magnitude. The difference of 0.8 megaelectron-volt between the binding energies of the two nuclides is attributed to the repulsive Coulomb energy between proton-proton in the helium 3,2 nuclei. It can be noticed that a pair of atomic nuclei, each of which would be transformed into the other by changing all its neutrons into protons and vice versa. Thus, nitrogen 15, containing 7 protons and 8 neutrons, is the mirror nucleus of oxygen 15, comprising 8 protons and 7 neutrons. Study of mirror nuclei has aided in showing that nuclear force binding protons and neutrons in the nucleus remains nearly the same when a neutron is replaced by a proton. Second is, nuclear forces have short range. The tiny size of nucleus its great stability shows that the forces operating among the nucleons inside the nucleus are very short range force. That is, they are effective over a very short distance. The short-range character of the nuclear forces distinguishes it from gravitational and electromagnetic forces, which act over large distances. If the range of the nuclear forces is larger than the dimension of the nucleus, they would have definitely affected molecular interactions. But no such effect has been observed in molecular structure. So two nucleons within about 2 femtometer of each other feel an attractive nuclear force. But outside about 3 femtometer, the nuclear force is essentially zero. We call the nuclear force short range because it falls to zero so abruptly with interparticle separation. Third characteristic is that nuclear forces are repulsive at very short range. At very short range of about 0.5 femtometer, nuclear forces become repulsive. If this was not the case, the nucleons inside the nucleus would collapse. Fourth is nuclear forces are very strong. Compared to electromagnetic and gravitational forces, these are very much stronger. They are stronger by a factor of 137 from the electromagnetic force and are stronger by a factor of 10 from gravitational forces. Nuclear forces are saturated. The range of nuclear force is limited. Saturation of nuclear forces implies that their interaction is only with the nearest neighbors. If the forces operating among the nucleons were long range, there would be interactions among distant nucleons in the nucleus, as well as between those in the close proximity. If each nucleon is interacting with all the remaining nucleons of a nucleus, then the total number of interacting bonds will be A multiplied by A minus 1 divided by 2. So binding energy will be proportional to A square, where A is a mass number. So total binding energy would increase roughly as A square. So we can see that it is almost constant in the range of A mass number more than 30 and less than 170, which confirms that short range and saturation property of the nuclear force. Each nucleon attracts those in its close immediate vicinity, but it is relatively indifferent to others. However, nucleons on the nuclear surface are not so completely bound and their nuclear force is not saturated. Sixth point is that nuclear forces are non-central. Gravitational and electrostatic force are central forces. That is, these forces act along the line joining the two particles or bodies. On the other hand, nuclear forces depend not only on the distance between the nucleons, but also on the angle between their spins made with the line joining the two nucleons. The nuclear force is known to be spin dependent. The two nucleons having parallel spin have stronger force between them as compared to those having antiparallel spin. This force depends on the angles between the spin and the orbital angular momentum vectors. Seventh characteristic is nuclear forces are exchange forces. Yakova in 1935 proposed a theory to explain the nature of nuclear forces. He proposed that when two nucleons are interacting, the cause of the force between the two nucleons is an exchange of a quantum between them. In other words, it means that the nuclear force is manifested by the exchange of force carriers. We will study now liquid drop model. First, we will see what are the similarities of drop of liquid and atomic nucleus. Nuclear forces are analogous to the surface tension of a liquid. The nucleons behave in a manner which is similar to that of the molecules in a liquid drop. In a liquid drop, the molecules are only influenced by their immediate neighbors. The surface molecules in a spherical liquid drop are not so tightly bound as their inner molecules. Same is true For the nucleons in a nucleus, the disintegration of nuclei by the emission of particles is analogous to the evaporation of molecules from the surface of the liquid. The similarities of drop of liquid and atomic nucleus. The absorption of particles by a nucleus corresponds to the condensation of liquid drops to a liquid drop, where the liquid density is independent of the size of the drop. Another thing is that the constant binding energy per nucleon is analogous to the latent heat of vaporization. The energy of nuclei corresponds to the internal thermal vibration of molecules of liquid drop. Now we will discuss the assumptions of liquid drop model. Bohr and Wheeler further developed the liquid drop model to explain the phenomenon of nuclear fission. Following are some assumptions involved in liquid drop model. First, nucleus is composed of incompressible matter. Nuclear force is identical for all the nucleons. In an equilibrium state, the nuclei of atom remain spherically symmetric under the action of strong attractive nuclear forces. Advantages of liquid drop model. The semi-empirical mass formula based on liquid drop model predicts the atomic masses and binding energies of various nuclei fairly accurately. Using liquid drop model, predictions can be made regarding nuclear stability with respect to alpha decay, beta decay, and spontaneous fission process. Liquid drop model also explains the basic features of the fission processes. Failures of liquid drop model. It fails to explain the extra stability of certain nuclei, where the numbers of protons or neutrons in the nucleus are 2, 8, 28, 50, 82 or 126. These numbers are called magic numbers. It fails to explain the measured magnetic moments of many nuclei. It also fails to explain the spin of nuclei. Also, the excited states in most of the nuclei. The agreement of semi-empirical mass formula with the experimentally observed masses and binding energies is poor for lighter nuclei as compared to the heavier ones. Practice question. Give the main characteristics of nuclear forces. How are nuclear forces different from gravitational and electromagnetic forces? Explain liquid drop model. State various assumptions of liquid drop model. For this presentation, we have taken some references. First, Introductory Nuclear Physics by Crane, Concepts of Nuclear Physics by Cohen, Introduction to Nuclear and Particle Physics by V.K. Mittal, and other different slides shared.